Hello.
Coucou.
We are already on YouTube.
Ah. What is? Oh, there is a live on YouTube.
Yes.
Coucou. Coucou. What is? Oh, there is a live on YouTube. Oh, Stéphane, je m'entends quand tu parles en écho.
Non. Yes, j'ai coupé. Il y avait le.
No fair. No fair.
Hi, Virginia.
Hi, I'm in my hotel room. I'm going to run upstairs and see if I can grab lunch, which happens to coincide exactly with this.
Okay, I think you have time.
So I'll be back.
Yes, of course. And Raphael, after I will record. So actually, then we will keep the recording. This is just for people now.
Fine. So I thought we could do a programming session for the last, the fourth lesson. What do you think?
Yeah, I think it's nice. Yes. Let's see, yeah, how people will arrive. In principle, we have a lot of people. We have, how many? 59. Now, in your course are...
Oh, nice.
50, 1 second, because also 54 in your course.
All right.
But some people, of course, will be there later, because, sometime, like my students now, they're in, some of them have class. So
all right.
It's hard to find a time for everyone. So I'm in Belgium, so actually.
Oh, what time is it?
Je suis en Belgique, Université de Namur.
Il est quelle heure là? Il doit être 18h?
18h, oui, comme en France. Tu veux faire... attends une minute, on fait un test déjà pour tes slides.
Je vais attraper un verre d'eau, d'accord? Je reviens tout de suite.
Oui, bien sûr. Olá, Nancy. Tudo bem?
Oi, Serrano, tudo bom?
Tudo bom. Quanto tempo? Estou na Bélgica, em Namur.
Sim. Está se livrando de um calor infernal aqui.
Me disseram que é terrível. Aqui tive calor quando eu cheguei, fiquei surpresa, mas agora já é inverno, friozinho, já começa.
Você vai ficar o semestre todo? Ou...
Sim, vou ficar, bom, semestre sim, vou ficar até, não aqui, mas na Espanha depois, até o final de fevereiro, mais ou menos.
Que bom.
Mas a gente deve fazer uma reunião com a Lisa, aquela da Universidade de Michigan, que trabalha num programa muito parecido com o seu. Somente
sei, eu sei. Eu tenho uma pós-doc minha, vai fazer um BEP lá, vou fazer um estágio de 1 ano lá com ela.
Ah, que ótimo.
Interessante. Isso seria bom. Eu quero ver se agora com esse mini curso eu aprendo.
Sim, a gente depois passa material.
Tá bom.
Vamos aprender. Aqui tem já a Virgínia, que é dos Estados Unidos. E tem outros, tem o Romano, que é aqui de Namur, o Matteo. Ele, por exemplo, trabalha na dinâmica do satélite. So we switch to English. So Matteo's Romano is Italian, but he works here in Namur. He's a postdoc. He works in satellite dynamics.
Aham.
And Hugo, I don't know. Hugo, where are you from? If it's possible to reply. De onde você é? Hugo. Não. Ó, acho que a pessoa fica um pouco tímida. Esperar. Tem um eco. Onde vai?
Acho que por causa do Stefanella.
Não, mas não é do meu, é de algum outro.
Hi. Hello.
Hello?
Hi.
Hey,
Okay. Now,
Um momento. Hello? So, more people from UFRJ. Leonardo from UFI. Rafael, Leonardo is working on topological data analysis. He is a topologist.
prazer.
Danielle and Fred were in the modeling class. Hello again. Vamos anotar. Hello, everyone. So there are some people not from Rio, not even from Belgium. Well, Rafael Nassi Garcia is from Unicamp. And she's very interested because she works on some statistical method to characterize a surface's property. So we saw that there are some people in Michigan. They use topological data analysis to study the surface roughness. So to compare a different technique, what is the advantage of one or the other. So she's interested in learning some.
Cool.
Yes.
Nice to meet you, Nancy.
Mariam is from Canada. Hello, Mariam. Where are you from in Canada? Which McMaster? Hi.
Yeah, I'm current McMaster.
Yes, great. You are in the mathematics or engineer, which there are several people from McMaster.
I'm from computational science engineering and interdisciplinary fields between math and business.
That's great.
Yeah, thank you.
Welcome. So we have some more students, some more people from UFRJ. Do you want to try to share the screen to see if it's... Yeah, perfect.
Full screen?
Yes, perfect. Victor, I will ask your help and try to help people
Yes.
in. Yes, so you are co-host, so you can let people in case
All right.
I don't someone. Okay.
Yeah.
Thank you. Okay, so I guess we can start 2 minutes. Okay, so I guess we'll start recording. Okay, so well, you can start sharing the screen, Rafael. So it's a great pleasure to have with us Rafael Tinoraj. And Rafael, it's French, but he loves Brazil. He did he did his studies in Paris at Orsay in Rien, Seclé. And now he's doing a postdoc at FGV in Rio. And he works at the boundary of many applications. He loves mathematics, in particular topology, algebraic topology. And he specialized since few years in topological data analysis. He gave wonderful courses. These were we all learning from him. So I'm sure this will be as good as the other. Please, Rafael.
Thank you, Stefanella. I have 1 hour, right? For this
Yes.
lesson.
Yes.
All right. Let me put an alarm. So good afternoon, everyone. I'm very glad to present this course about TDA, topological data analysis. So that's quite a new theory that takes its roots into in algebraic topology, right? The idea is to apply common ideas of algebraic topology from the last century, apply these ideas to data analysis. So in these 4 lessons, this will be mostly mathematics that I will present, but I try to put a few concrete data analysis problems as often as possible. And we will actually start with a few examples to motivate and introduce the philosophy behind this theory. The first example comes from chemistry. 30 years ago, there is an important question in chemistry. That is the conformation space of molecules. The conformation of a molecule, could say configuration, is the spatial configuration it has, because each atom of the molecule has some degree of liberty, right? But because of the physical forces, not every position is possible. So in this paper, they studied this famous cyclooctane molecule. It's a molecule made of 8 atoms of carbon and 16 of hydrogen. In order to understand the possible configurations of the molecules, they did the following. They tried to record the spatial position of each atom. So this molecule contains 24 atoms, and each one has 3 Euclidean coordinates, right? So you get, in the end, from a molecule, 3 times 24, 72 coordinates. That is, you can transform one molecule that you observe into a point with 72 coordinates. So that's a point in R72. So what they do, they take a lot of molecules and they transform all these molecules into the corresponding points in R72. By doing that, what you get in the end is a bunch of points. We say a point cloud. I've heard the recording stopped. Should I continue? I will continue. So this,
Fanella just fall off. The Fanella is not in the room anymore.
oh, I think it's fine.
Yes, yes.
Sounds good.
Okay. So you obtain from a bunch of molecules a bunch of points, and the third try to study the shape of this point cloud. And what they discovered is that it's not any random point cloud. It's actually a point cloud that is very close to a shape. And this shape is the union of a sphere here and a Klein bottle embedded in this high dimensional space. And actually, you can map properties of the molecules with their position in this configuration space. Molecules being at the intersection of the Klein bottle and the sphere being critical configurations of these molecules. By the way, if you have any question, any comment, please interrupt me. I would be happy to answer. Another example from biology. So we have in our brain what is called grid cells. There are special neural cells that has been studied a lot lately. These cells are responsible for our understanding, visualization, spatial visualization of what is in front of us. And so there is this idea that what we see, what we observed, is encoded in these grid cells, and then kind of create a map of what we see. And that they had this idea that the grid cells, the way they interact, should have a torus structure, right? In order to observe that, they did this very nice experiment. So you will record the activity of a lot of grid cells. To do that, you can use what is called the neuropixel. It's a technology that allows to record one cell at a time. You know, the neural cells, they emit spikes. So you have a bunch of time series, the activity of each neuron. And by comparing this time series, you have a distance, right, between the grid cells. So you kind of create a metric space, right? And they computed the topology of this space. And what they obtained was a torus. A last example from medicine. So this is about the breast cancer, a very complicated cancer with a lot of different types. It's not clear how we can categorize the different types of breast cancer. What they did here, kind of the same idea than the first example. They transformed each patient contaminated by breast cancer into a point, a vector, here of 262 coordinates. These coordinates being genomic variables, that is genetic information about the patient. So if you take one patient, you get 1 point. If you take a lot of patients, you get a lot of points. And they studied the topology of this space. And it ends up that this point cloud, so in R262, a lot of dimensions, has the shape of a tree. And actually, you can study further the structure of this tree. It has 3 distinct branches where you can observe different kind of breast cancer. And they discovered at the end of this branch a group that was not known at this time, a group of patients that synthesize a particular molecule, protein, CMYB+, and they have the property that this group do not die from the cancer. They all survive. So they gave the name CMYB+ to this group. So what I try to show here is that in TDA, what we try to do is understand the, let's say, underlying topology of our data set, and hope to find some interesting information, some hidden structure behind it that will help us in our analysis. From the theoretical part, TDA is at the center of algebraic topology, computational geometry, and data analysis. So what I will focus mainly is algebraic topology in these 4 lessons. And this is the plan of this mini course. Today, I will introduce the main objects of topology and algebraic topology. In particular, topological invariants. These are what helps us understand topological spaces. In 2 days, I will introduce homology, which will be the stronger invariant we'll use. Next week, we'll have to wait next week to talk about persistent homology, right? And then I propose a few a Python programming session altogether, so we can play with these ideas. All right. So for today, let me introduce the main protagonists of topology. I have a few historical recap. I wanted to talk a little bit about the history of topology. So it's common to say that topology starts with Euler in the 18th century. If you understand topology as the theory that studies shapes that you are allowed to deform, right? This year, he published his famous Königsberg bridge problem. That is basically topology with graphs. A century later, you had Mobius that started to study surfaces. So you can think about graphs as one-dimensional shapes and surfaces as two-dimensional shapes, right? And in order to study these surfaces, he introduced already some ideas of invariant. Then we had Riemann and Betti, kind of the same moment. They studied the same ideas of topological invariance. At this time, they talk about connected components, genus. Betti, he defined the Betti numbers, right? But we'll have to wait the end of the century to have the first real formalization of homology and homology groups, right? With Poincaré in this extremely famous paper. So Poincaré defined homology. He defined homotopic groups, and he had this question about homology groups. He asked whether they were strong enough to determine if a shape is a sphere or not. And this became the famous Poincaré conjecture, right? That has been solved a few years ago by Perelman. I mean, not Perelman only, of course, it's a lot of mathematicians behind it, but he's been famous for this. All right. So what is topology about? The two main characters of topology are the topological spaces and the continuous maps. So topological space, this is the biggest abstraction of a concept of space. I won't read the definition, but basically it's a topological space is a set of points with an additional structure, a structure of neighbors, a structure of proximity. Once you have this abstract definition of topological space, you can also define abstractly what is a continuous map. So the formalism involves what are called open sets. And you can see here that a map between two topological spaces, the definition of continuity can be expressed only with the notion of open set. But for those who never saw that, it's not a problem, because topology in this formalism already contains the usual epsilon delta topology we study. When I talk about topological space, you can think of subsets of Rn, the Euclidean space. If you do so, then this definition, this mysterious definition of continuity, is equivalent to the famous epsilon delta definition of that we all know, right? So let me explain how, in practice, we can build topological spaces. This will be the opportunity for me to introduce important spaces. So as I said, you can define a topological space just as a subset of the Euclidean space. All right. So for instance, in Rn, I can define the unit sphere. This is a set of points at distance 1 from the origin. I can define the cube. So this is the same thing, but with the infinite norm. Open balls, closed balls. So you have a lot of subsets of Rn, right? And they do not admit a nice algebraic description as those, right? So that will be a problem for us. Topology will help us to study spaces that are not even nicely definable like this. So first possibility, as a subspace of the Euclidean space. Another way to build topological spaces is by gluing together other topological spaces. So for instance, here I took two lines, two arcs, and I decided to glue the extremal points, the two pairs of boundary points, right? So what does that give me? It gives me a circle. Two arcs glued, this is a circle. Actually, you can do it in any dimension, this construction. If I take two disks, two hemispheres, and I glue the boundaries, I obtain a sphere, right? A two-dimensional sphere. I can do it for the three-dimensional sphere also. If I take two balls, two closed balls, and I glue the boundaries, I obtain a three-dimensional sphere. So this is a bit harder to visualize because the three-dimensional sphere is, we cannot see it in our three-dimensional space, right? But we can formally do. I mean, this is a nice way to see it. Close to the notion of gluing is the notion of quotient. So basically, a quotient will be a gluing of a space on itself. Here I took the famous example of the square. I take this square and I wish to quotient, to glue the opposite side. All right. In topology, everything is made of rubber. Everything is deformable. So this square, I can do like that, up, and glue the two opposite sides, and this gives me a cylinder. Okay. I can go further. I wish to glue these two opposite sides, but also the other pair of opposite sides. So I first glue the first pair, I get a cylinder, and then I have two boundary circles that I want to glue one onto each other, onto the other. And if I do that, I can deform a little bit, and in the end I get a torus. I hope this is clear. Interrupt me if not. We can play a lot with this construction. What I draw here is the square. I want to glue the opposite sides, but in the opposite direction, in the opposite sense. So I take my square, and then I twist before I glue. And this gives me the Mobius band, right? If you want to glue again the other pair in the same sense this time, what I get is a Klein bottle. It's a bit harder to visualize, but it's possible. Last gluing that we can do on this square is I glue both pairs of opposite sides, exchanging the sense both times. Does anybody know what I obtain with this construction? What famous topological space I get?
Can I take a guess, maybe?
Sorry, so again?
Can I take a guess, maybe?
Yeah, please.
Some type of, I don't know, projective plane or something?
Yeah, exactly. Yeah, yeah.
Okay.
Yeah, you get the projective plane. Thank you.
Oh, thanks.
All right. So now our question is, how do we do in topology to understand all these spaces? So as I said, the philosophy behind it is that everything is deformable, right? So what I will try is to define formally what is a deformation. And actually there are two common definitions we can use. Is the relation of homomorphism and the relation of homotopic equivalence. So this is what I will introduce right now. I will start with homomorphism. The one I prefer is the relation of homotopic equivalence, and you will understand why later. Let's start by comparing spaces with the homomorphism. So I will use in this course every time the same notations. X and Y will be topological spaces. And I consider a map F that goes from X to Y. F is called a homomorphism if it is a bijection, it is continuous, and its inverse is continuous. Okay? You could say that a homomorphism is bicontinuous bijection. If you can find, if there exists a homomorphism between two spaces, then we say that they are homomorphic. Okay? Here I gave an example. The unit circle in the plane and the square are homomorphic. How can I prove that? I have to define homomorphism. And I took this very simple one. Each point of the circle I map to its projection onto the square. Okay? So this is a well-defined bicontinuous bijection, and we conclude that they are homomorphic. Actually, let me show you. It is a general property that the circle will be homomorphic to any closed loop, right? I can deform things like that. The circle is also homomorphic to a triangle, right? It's not complicated to define a homomorphism like that. So what we are allowed to do with homomorphisms are continuous deformations. The circle and the interval are not homomorphic. I cannot find a homomorphism between them. Why? It's not easy to prove. I will give you a proof of this by the end of this lesson. But for you to get an idea, in order to define a bijection first between the circle, a continuous bijection, and the circle and the interval, I will have to break the circle, right? I will have to cut the circle. And this is not a continuous operation. This will not yield homomorphism in the end. Last example is this very beautiful theorem of Bauer that says that the Euclidean spaces Rn and Rm are homomorphic if and only if the dimensions agree, and if and only if n equals to m. So in particular, the plane here is not homomorphic to the real line. Okay. Oh yeah, no. Also another example: classification of surfaces, as I said, already studied by Mobius. If you take an orientable surface, you can show that this surface up to the you can show that this surface up to deformation is homomorphic to one surface of this list, and this list is indexed by what is called the genus, right? The sphere has genus 0, the torus has genus 1, the bitorus has genus 2, etc. All right, and so what do we do? Now we have this relation. This relation of being homomorphic is an equivalence relation. So we can consider the quotient set. We can consider the equivalence classes of this relation. What is an equivalence class? For instance, what is the equivalence class of the circle? It is the set of all the spaces homomorphic to the circle. So I have the circle, I have the square that is homomorphic to it, we've seen it, the triangle, this polygon, any polygon actually. I will put in this class all spaces homomorphic to the circle. We have also the class of the lines, the intervals. We've seen before that the circle is not homomorphic to the line, right? So these classes are disjoint. We have the class of crosses, class of spheres. I mean, there's an infinite number of classes, of course, of equivalence. An important question here, when we write a list like that, is to verify that the classes are actually not the same, and this is not a simple question. The aim of algebraic topology is to give tools to study this kind of questions, and the main tool we will use is invariant. But before that, I'd like to talk about our second relation between topological spaces, and this is the equivalence of homotopy. First, I have to define what is a homotopy between maps. I have, again, two topological spaces, X and Y, and this time two maps, two continuous maps, FG from X to Y. A homotopy between F and G is a map, a big F, like that goes from the product of X and 0, 1, and goes into Y. You can think of 0, 1, the interval, as the time. If you take time equals to 0, then the restriction of this map must be equal to F. If you take time equals to 1, then the restriction must be equal to G. And the whole map, F, must be continuous also. If you can find a homotopy between two maps, you say that the maps are homotopic. So what does that mean? It's simply a continuous interpolation between F and G, right? For instance, here I took the map F. This is a 0 map from R to R. Here is this G sinusoidal kind of map, like this. And my homotopy, you see, it's simply this linear interpolation between F and G. Let me give you another example. The map F now is a map from S1, the circle, to the plane, and this is simply the usual the embedding of the circle, seen as a subset of the plane, right? And my second map, G, is also an embedding of the circle, but translated, right? Now the center of the circle is the point 2, 2. And I can define a very simple homotopy between F and G. Simply this translation, right? You have this parameter T here between 0 and 1. And I say the image of xt is cos theta plus 2t and sinus plus 2t. So as you may understand here, when the codomain is the Euclidean space, everybody is homotopic, actually, because you can do linear interpolations. It's interesting, the notion of homotopy, when the codomain is not trivial. Let me give you an example. Here, I consider the same maps, F and G, but now the codomain is, I removed the origin, okay? It's R2 minus the point 0, 0. I use the same definitions of F and G. And now, my homotopy is not well defined. Actually, don't have homotopy between F and G, because if you want to translate this circle to the center 2, 2, you will have to cross this point, but the point does not belong to the space, right? So it's impossible. It's not easy to prove that there is no homotopy between F and G in this space. You will need a few tools that we will introduce later. Okay. And now I can talk about homotopies between spaces. X and Y, our two topological spaces. A homotopy equivalence between X and Y will be a pair of maps, F and G. Now F goes from X to Y, and G goes from Y to X. And I call this pair homotopy equivalence if the composition GF, so this is like this, so GF, it's a map from X to X, if this composition is homotopic to the identity map on X. And I also ask that the other composition that goes in this direction, FG, is homotopic to the identity map on Y. Okay? This may look a bit mysterious, this definition at first, but it's not. It really is a weaker form of homomorphism. Because if you think about being homotopic as being equal, as being the same, then you just ask for the first composition to be the identity and the second composition to be the identity. And this is exactly the definition of a homomorphism, right? A homomorphism is a map F that admits an inverse, right? And when you have an inverse, then the compositions are equal to the identity. As a consequence of this observation, homomorphic topological spaces are homotopy equivalent, right? Being homomorphic is a stronger condition. Being homotopy equivalent is a weaker condition than the other. So what actually happens with this homotopy equivalence? With respect to the homotopy equivalence, we are allowed to deform the spaces, right? The circle is homotopy equivalent to the triangle. I mean, they are homomorphic, right? So they must be homotopy equivalent also. But we can do more. What we can do is to retract pieces of our spaces. For instance, this circle with a little hair here, I can take the hair and retract it. and what I get is a circle. Same thing with this annulus. If I take the annulus and I retract, right, all around onto the inner circle, then I obtain this circle, and all these spaces here are homotopy equivalent. The line is homotopy equivalent to a point because I can retract it. The letter A is homotopy equivalent to a triangle because I can take the legs of A and retract it. I cannot cut this. This triangle is not equivalent to a point. I will have to retract. It's not possible, right? Okay, so this was a lot of definitions. But we can do the same as what we did with homomorphism equivalence. We can gather the spaces into homotopic classes. Now the classes are wider, they are bigger, because given the space, you have more homotopy equivalent topological spaces. For instance, in the homotopy equivalence class of the circles, I have the square, I have the circle, but I also have the letter Q, I have the annulus, I have deformed annulus, you know, a lot of spaces. The class of points now contains a lot of spaces. Actually, all the spaces contained in this class are called contractible spaces. That are the spaces that you can contract on only one point. The class of spheres, the class of the torus, etc. So I have a little exercise for you to verify that it was clear enough what I explained. These are the letters of the alphabet. I'd like you to classify the letters into homotopy equivalence classes, right? Gather the homotopy equivalent letters, and then you tell me how many classes you obtained. I give you 2-3 minutes, something like that. You can ask me questions if you wish.
There is an answer in the chat.
Oh, let me see. Andre found 3 classes. Yeah, this is the answer. Can you tell us, Andre, what classes you found?
I think I can say like A, B, D, R are all from the same class, and then B, it's longing in another class, and the other letters is another class.
Yeah, exactly. This is it. You have 3 classes. The first one are the letters that are a circle, homotopy equivalent to circle. You have B alone, as you said. This is a space that is homotopy equivalent to the union of 2 circles, right? It has 2 holes. And then you have all the other contractible letters. Thank you. Any question about that? All right. So let's continue. We have defined topological spaces, continuous maps, and our 2 equivalence relations, the homomorphism equivalence and the homotopy equivalence. I will now talk about topological invariance. And I could introduce the problem like that. We have classified spaces into groups, right? So let's say for the homotopy equivalence or homomorphism equivalence. These are the same questions. Human questions. Given a new space, X, that you are studying, how do I know in which class it belongs? This may be a complicated question. You have to find a homomorphism or to find a homotopic equivalence. Another question is, given a class, given a group, what are the common characteristics? What are the common features of the spaces in this group, right? As we've seen, this B here, it shares with the two circles the fact that it has two holes, right? This question could be related to this observation of Poincaré in this very nice book. He said, math is the art of giving the same name to different things, which is exactly what we are doing here, right? I will introduce today 4 invariants, 4 properties, 4 characteristics. The first one is embeddability. Say we have a topological space X. I say that X is embeddable in Rn, the Euclidean space, so N is part of the definition, if there exists a continuous injective map from X to Rn, right? What that means is that I am able to draw my space in the Euclidean space. For instance, the interval 0, 1, open here, but it can be closed, whatever, is embeddable in R because I can draw the interval in R. I can see the interval as a subset of R. So this is very easy. The circle is not embeddable in R, right? If I want to define a continuous map, like injective continuous map, it's not possible. I will have to pass twice on the same point. Now, I will give you the invariance property of embeddability. It's a property that we'll see for every example. It is the main property that it is maybe a definition that an invariant has. If two spaces X and Y are homomorphic, then either they are both embeddable, either no one is embeddable into Rn and being fixed, right? So the property of being embeddable in Rn is a characteristic shared by all the spaces in the same homomorphism class. And we say that being embeddable in Rn is an invariant of homomorphism class, right? This is very useful to show that two spaces are not homomorphic. If you can show that one is embeddable and the other one is not, then this proves that they are not in the same homomorphism class. I can use that to prove a not so trivial fact that the cylinder and the Mobius strip are not homomorphic. They look alike, right? It's a strip like that. The Mobius strip I twisted before gluing. So to show that they are not homomorphic, I will embed one into R2 and show that the other one cannot be embedded in R2. And of course, the one that we embed in R2 is the cylinder, right? If I take my cylinder and I open it, I squash it like that on the plane, what I get is an annulus, a ring, right? So I have a well-defined embedding of the cylinder in the plane in R2. Now I will prove that the Mobius strip cannot be embedded in R2. To do this, I will draw two circles on the Mobius strip. So you have to trust me, or to trust this drawing, that these two circles here that I draw only intersect once at this point, right? Now, let's suppose, by contradiction, that I can embed the Mobius strip in R2. So this is an injective map. So in particular, what I obtain are two circles in R2, two closed curves that only intersect once. But well, you see, I mean, in the plane, if you enter the circle once, you have to go out. Otherwise, you cannot be closed. This is actually a consequence of the very strong Jordan's theorem about closed curves in the plane. We conclude that this embedding did not exist, and that these two spaces here are not homomorphic. All right. Yeah. Embeddability is an invariant of homomorphism classes, but not of homotopic classes, right? The cylinder and the Mobius strip are homotopy equivalent because I can retract both spaces into their inner circle. They are both homotopy equivalent to a circle.
There is a question once in the chat.
Yeah. Let me see. Why cannot the circle just touch in one point? So I'm talking about, you mean like the tangent? No, because why is it not possible?
Because of the inversion of the when you
Sorry?
For the inversion, no? I see at a certain point they have to be inverted, at least at the
How to make this idea?
for the construction.
They cannot be tangent at only one point. Yeah, right. It's not obvious. You can.
They are tangent in all the points or the cross. They cannot be tangent in one point. This is
Yeah. But it's not that obvious to see.
To prove
you have to prove that if they cross here, then you have to prove that here they also have to cross. It is not enough to be tangent. So there is a reasoning. You're right. It's not obvious.
Leonardo is giving you a hint.
Let me see. So, could we introduce the ideas of sides of a circle in the surface? Not really, because the Mobius strip, it does not have one side, you know. The Mobius strip, when you travel, you end up on the opposite side. So, I think it is more a question of let's say it's not I cannot see it directly, but there is a little thing to prove. Yeah. Thank you for the
next time.
So embeddability is not an invariant of homotopic classes because, as I explained, both spaces here are homotopic equivalent to circle, but only one of them is embeddable. Okay. I have a little connection with applications. So if you can think about the property of embeddability as the problem of dimensionality reduction in the applications. So this comes from this very nice paper. You have a cylinder in the three-dimensional space, and you want to project it in the plane injectively, right? So you can see that a few famous algorithms, does not respect the topological structure you had at the beginning, but these two algorithms in the end were able to squash, to embed the cylinder in the plane. Let's talk about another invariant, the number of connected components. I say that a topological space X is connected if for every pair of points, X and Y, you can find a path between X and Y. What is a path? It's a continuous map from 0, 1 to X, such that the F0, the initial point, is X, and the final point is Y. For instance, this space is connected because you can connect X and Y. This is not a connected space because in order to connect X and Y, you have to go out to exit the space. And so you cannot define this continuous map. When your space is not connected, you can define its connected components, right? The connected components are the largest connected subspaces of my space. For instance, this space X here has 4 connected components, right? These 3 disks and this line. And now the invariance property. If 2 spaces are homotopic equivalent, then they have the same number of connected components. So being the number of connected components is an invariant of homotopic classes. Consequence, if 2 spaces are homomorphic, then they are homotopic equivalent, and then they share the same number of connected components. And just as before, we can use this property to prove that 2 spaces are not homomorphic. For instance, the interval 0, 1 and the union of 0, 1 and 2, 3, these spaces are not homomorphic, neither homotopic equivalent, because the first one has 1 connected component and the second one has 2 connected components. I can use this property also to show, as we said at the beginning, that the interval and the circle are not homomorphic. How can I prove that? They both have 1 connected component. So we'll use a very nice construction. I will prove this by contradiction. Let's suppose that these spaces are homomorphic, right? So I have a map F from the interval to the circle, all right? A homomorphism. What I will do is pick a point, X, on this interval, and look at its image, F of X, right? And now I will remove these points from the spaces. If I consider the restriction of F, I call it G. G is a map from 0 to pi minus X, and the circle minus F of X. And G is a restriction of a homomorphism, so this is still a homomorphism. You can prove this. But now, look at these spaces. The interval minus a point. This is two intervals, right? And the circle minus a point. It's an open circle. Two intervals. This is two connected components. An open circle, it's one connected component. So what I did here is I defined a homomorphism between a space with two connected components and one connected component. This is impossible. And so by contradiction, the initial spaces are not homomorphic. All right. I have a question for you for the next lesson in 2 days. I want you to prove that the interval, the semi-open interval, and the open interval are not homomorphic, right? Based on these same ideas, using the number of connected components. A glimpse at applications. Connected components. This is related to the problem of classification in data analysis. Say you have a data set like that, any correct classifier would find these two groups, right? These two clusters. What happens in TDA is that we think of these two clusters as two connected components. We think of this point cloud as sampled on underlying space. This space is made of two components. And so in the end, classifying your data set is equivalent to finding the connected components of the underlying space, right? This is the general philosophy of TDA. I think I have only 5 minutes left. I will go quick on this.
It can be 10 minutes, we start later.
Yeah, all right. Fine, let's say 10 minutes. This is enough. So, another characteristic, this is Platon. These are the famous Platonic solids, right? These polyhedra share a very nice property. If you take the number of faces, that you subtract the number of edges, and you add the number of vertices, right? 4 minus 6 plus 4, it's equal to 2 for all the polyhedra. This number here is called the Euler characteristic. And he proved that in general, in any polyhedron, convex polyhedron, this alternate sum will be equal to 2, right? So there is some combinatorial regularity behind polyhedra. What we like to do is to generalize this Euler characteristic to any spaces, not only polyhedra, not only surfaces. And to do this, we need the notion of simplicial complex. So simplicial complex, I will use it a lot in the next lesson. So let me introduce it right now. Simplicial complex is the object we use to encode topological spaces on a computer, basically. It's a combinatorial structure, a generalization of a graph. It's like that. You have a set V called the set of vertices, a simplicial complex over V. It is a collection of subsets of V. All right? These subsets of V are called simplices. And you have only one axiom, that if you have a simplex and a subset of this simplex, it must also be a simplex. Let me give you an example. The vertex set 0, 1, 2. I define the simplicial complex K that is made of the singletons 0, 1, 2 and the pairs 0, 1, 1, 2, 0, 2. By convention, we use these square brackets and not the curly brackets, but to denote simplices, but there are subsets. And so what is this? We can actually draw the simplicial complex. These singletons, we see them as points, vertices, right? So I have 0, 1, 2. And the pairs, I see them as edges. I have the pair 0, 1, the pair 1, 2, and the pair 0, 2. So this simplicial complex encodes a triangle, right? By definition, the dimension of a simplicial complex is the highest dimension of its simplices, and the dimension of a simplex is its cardinal minus 1. So here the dimension is 1. And topologically, this triangle, this is a circle, right? So we encoded the circle as a combinatorial structure. Another example, now have 4 vertices, and I consider all the singletons, all the pairs, and all the 3 tuples, right? This gives me a tetrahedron. And the tetrahedron, this is topologically a sphere. So we can represent the sphere on the computer thanks to this simplicial complex. Now I can mimic the definition of the Euler characteristic. I will say that the Euler characteristic of a simplicial complex is its number of vertices minus its number of edges plus its number of triangle minus its number of 4 tuples, etc. For instance, for the circle, the triangle, this is 3 minus 3, 0. For our tetrahedron, this is 2, right? As we've seen at the beginning. There is another question. We'd like actually to define the Euler characteristic not for simplicial complexes, but for topological spaces. In order to do that, you have to use triangulations. So a triangulation of a topological space is a simplicial complex that is homomorphic to it, right? So if I take my circle, I encode it as a triangle, and so I can define its Euler characteristic. There are some complications with what I've wrote here, because given the topological space, is the triangulation unique? Does it actually admit a triangulation? We will ask these questions next week. The Euler characteristic is something that indicates how many holes my space has, something like that. It's been used in the context of the study of the cosmic web, right? The cosmic web, this is a very interesting object because it can be seen as a one-dimensional object. If you see stars as if you see strings of stars, this is a graph. It can be seen as an object of dimension 2. It can be seen as an object of dimension 3 if you separate into galaxies. And understanding the topology of the cosmic web, this is an interesting question. What they have done here is they calculated the Euler characteristic of the cosmic web. This is actually a famous topic in TDA. More about that, more about the cosmic web later in this mini course. So we'll finish very quick with the Betti numbers. Our last invariant. given a topological space, you can define a sequence of integers associated to this space, beta 0, beta 1, beta 2, etc. These integers are called the Betti numbers. The Betti numbers, they gather a lot of information about the space. And their construction is not this simple. It's based on the theory of homology that we will see in 2 days. So instead of defining it formally, I will show you how it looks today. I took 5 topological spaces and I wrote the first 3 Betti numbers. All right. Actually, it's not hard to understand them. The first Betti number, beta 0, is equal to the number of connected components of the space. So all the 4 first spaces are connected. So 1 connected component. And so beta 0 equals 1. Except the last one, which is made of 2 circles. So this is 2 connected components, right? Beta 1, this is the number of holes in my space. What is a hole? Basically a circle, right? This is the hole drawn by a circle. So these 2 circles here, tangent or not, they have 2 holes, right? The sphere does not have a hole, it has a void, right? A void being like the 2-dimensional equivalent of a hole, right? Another example, the torus. The torus has beta 0 equals to 1, right? It has 1 connected component. Beta 2 is equal to 1 because it has 1 void inside, like a sphere. And beta 1 is equal to 2 because it actually has 2 inner circles, 2 independent inner circles, right? That you can see here. And we have, of course, the invariance property that homotopy equivalence spaces share the same Betti numbers, right? So this can be used, again, to have an idea if 2 topological spaces belong to the same class, and it can help us to show that they are not in the same class. I think I will stop just this example to finish. That really gives a taste of TDA. This is a very famous paper. The authors study the space of natural images. So what they do, they take a huge collection of images and they extract 3 by 3 batches, right? 3 by 3 little images. The images are in grayscale. So in the end, a patch like that is simply a point in R9, right? The grayscale is between 0 and 1. So you take a lot of images. You obtain a lot of points. This is a point cloud. And what they did, they computed using TDA the Betti numbers of this space, right? Of the underlying space. And what they found are the following numbers. Beta 0 equals to 1, beta 1 equals to 2, and beta 2 equals to 1. And then what we usually do when we see something like that is we think, well, I know spaces that have these Betti numbers. What spaces do I know? The torus, right, we've seen, but the claim bottle also. The claim bottle, unfortunately, has the same Betti numbers as the torus. And the authors verified that the points actually lie on a claim bottle, an embedding of the claim bottle. And this idea has been used later to design a claim bottle-based algorithms for image analysis. So this is it. We've seen today a basic notion of topology. relations between topological space and how to understand the equivalence classes coming from these relations through the notion of invariant. And this is it for today. Thanks a lot.
Thank you.
Excellent, as always. So let's thank Raphael. So open the microphone and join me.
Thank you.
So
Thanks, teacher.
question, please.
So I have a question, like I have two questions actually.
Yes, please.
Like the first one, like regarding the Euler characteristic, because I mean, is it a good measure also to, I mean, how useful is it as a measure of equivalence between two spaces? Because I mean, you talked that you said that the Euler characteristic of the circle is 0, right?
Yeah.
If I'm not mistaken, the torus also has Euler characteristic equal to 0, right?
Yeah. No, this
like,
is.
what does it mean? Like, well, because they're not equivalent that much.
Yeah. No, this is a weak invariant compared to homology. Homology will help to discriminate between these two. But what is interesting with the Euler characteristic is that it's very simply defined. It's just this alternate sum. And for instance, in the classification of surfaces, right? I explained that they are classified by genus.
Yes.
Actually, they are also classified by their Euler characteristic. What I mean is that if you restrict your analysis to surfaces, then Euler characteristic is enough.
I see. Okay.
But in the whole world of topological spaces, and this is weak.
Okay, I see. Makes sense. And the other one is like when you talk about the Betty numbers of the torus and the Klein bottle.
Yeah.
So that I mean they're, I mean, you can find a homotopy between them.
No. The same way that the circle and the torus have the same Euler characteristic but are not equivalent. The torus and the Klein bottle have the same Betty numbers but are not equivalent.
Okay, I see. Because I mean the Klein bottle is orientable, right? I believe, or not?
It is not orientable. Yeah.
It's not orientable. Okay, then yeah, that makes sense. Sure.
But you could, I mean, there are other invariants you could use. Actually, we will study, with homology. Next time, we will be able to discriminate between these two spaces.
Okay, I see. That's fine. Well, thanks.
Thank you. Virginia asked for if my slides will be available. They are already available on my website. If you go, if you go to rafaeltinaraj.github.io, and then you go to talks, and then today's talk, you can click on the slide.
Great, and of course, you will have also the recording. So yeah, it was very clear as usual. So any other question? It was so clear that I don't have more questions. So we are very much looking forward for the next lecture on Thursday. Thank you so much, Raphael.
Thanks to you.
And I do remind you that Raphael is looking for a job, possibly in Rio. So professor, they are online. Take good notes of this. Okay. Thank you, Raphael, very much. And see you next lecture. Bye-bye to everyone. Thank you.